A soft miniaturized continuum robot with 3D shape sensing via functionalized soft optical waveguides. In this paper, we present a fully soft miniaturized continuum robot that integrates 3D optical shape sensing through functionalized soft optical sensors, representing a simple, low-cost, versatile sensing solution with the potential of multiple applications in soft robotics. Our continuum robot features 3 actuation channels with 3 cables running inside them. 2 soft optical waveguides are placed in a cross configuration. Each waveguide consists of a functionalized, optically clear polyurethane medical tubing. For the sensor fabrication, 2 sections of tubing are patterned by using a laser precision micromachining system. The patterning consists of creating 6 V-shaped cuts on the upper surface of the tubing. In order to place the tubes in a cross configuration, 2 soft aligners are fabricated by pouring silicon into 3D printed molds. The aligners contain 4 holes each to accommodate the waveguides, and their aim is to maintain the 2 loops in place. After demolding the aligners, each waveguide is looped into them, making sure that the 2 patterned surfaces are orthogonal to each other. 4 stainless steel rods are inserted into each of the 4 waveguide ends as a core support for the next molding step. The sensor is then inserted in a 2-half cylindrical mold along with the 3 pins that will create the actuation channels. Silicon is poured inside the mold and cured. Finally, the robot is demolded. 3 cables are inserted in each actuation channel and secured at the tip with adhesive. The sensor follows the laws of optical theory by carrying light by total internal reflection. We introduced an anisotropy only on one side of the sensor surface in order to easily monitor its sensitivity to bending. In our case, the waveguide has a core made of polyurethane tubing interfacing with 2 claddings that are the silicon surrounding the tube and the internal air channel. This unique characteristic allows an exceptionally high baseline signal even at a small sensor scale. When the robot bends in the direction of the patterned region, the V-shaped cuts will gradually close and more light will be transmitted through the tube, leading to an optical gain. Instead, when the robot bends in the opposite direction, the cuts are going to gradually open and more light will escape through them, resulting in an optical loss. To calibrate the robot, 3 servo motors were connected to 3 actuation cables. The sensor data was collected by a DAC system and the position of the robot tip was acquired by an EM tracker. To model the robot shape, a constant curvature modeling approach was utilized by mapping the tip coordinates XYZ to the R parameters K and phi. The robot was calibrated by actuating in the 3D space, collecting data points of the sensor readings and the corresponding tip coordinates. 4 distinct sections can be found in the workspace depending on the different combinations of the waveguide responses. In these sections, phi and R can be mapped as unique surfaces. Here we show the 2 surfaces used for the sensor validation. An accuracy test was performed by programming the robot to follow a specific path through a range of phi and R values. The predicted position of the 2 parameters was compared to the actual true values acquired by the EM tracker. The average error was 3.08 millimeters. As a validation, the robot was actuated in a section of the space, and its predicted shape was plotted on a MATLAB user interface in real time, showing an accurate shape sensing prediction. We presented a soft miniaturized continuum robot able to provide optical shape sensing and tip tracking. We developed a laser precision micromachining patterning technique to functionalize off-the-shelf medical tubing by creating a sensor with bidirectional response to bending. We finally demonstrated the accuracy of our system with a 3D real-time shape sensing validation.